What could possibly be the most powerful force in the vast universe? Think about that for a moment. We're talking about a cosmos so immense, so filled with wonders beyond our wildest imagination, black holes that warp space-time, galaxies colliding in cosmic dances, invisible dark energy pushing the universe apart at unimaginable speeds. Yet even among these titans of nature, there might be something even more extraordinary, something so potent it defies comprehension. And today, we're going to uncover what that might be. Picture this: you're floating in the infinite void of space, surrounded by the sheer magnitude of existence. Stars flicker like distant campfires, nebulae swirl in vibrant hues, and somewhere out there, forces are at work that shape the very fabric of reality. But what lies at the heart of it all? Is it the crushing gravity of a black hole where not even light can escape, or the mysterious pull of dark matter silently holding galaxies together? Maybe it's something even more elusive, a force so fundamental, so utterly dominant, that it makes everything else seem insignificant by comparison. This isn't just about listing cosmic heavyweights, it's about diving into the unknown, peeling back the layers of the universe to reveal its deepest secrets. And here's the thing, the answer might surprise you, because power isn't always about sheer force or size. Sometimes it's hidden in the tiniest particles or woven into the very laws that govern existence. So buckle up. We're about to embark on a journey that will take us from the smallest scales to the grandest cosmic arenas, uncovering what truly holds the title of the universe's most powerful phenomenon. And trust me, by the end, you'll never look at the cosmos the same way again. Power in the universe isn't what we typically think of when we hear the word. On Earth, power might mean a roaring waterfall, a bursting volcano, or even the energy trapped inside an atom. But out there, it's on a whole different level. To understand cosmic power, we have to redefine it. Here, power isn't just about strength, it's about transformation. The ability to rip apart stars, bend space-time, or even rewrite the rules of physics itself. Take something as familiar as a hurricane. Here on our planet, it's one of the most destructive forces we know, winds howling at over 150 miles per hour, tossing cars like toys. Now imagine that same energy, but multiplied by 1 billion. That's the kind of raw power we're dealing with when we look at a supernova, where a dying star explodes with enough force to outshine entire galaxies for weeks. In a single instant, it unleashes more energy than our sun will produce in its entire 10 billion-year lifetime. That's not just power, that's cosmic power. But destruction is only one side of the equation. True power in the universe isn't just about tearing things apart, it's about building them too. When galaxies collide, it's not just chaos. Those titanic clashes forge new stars, new worlds, even new possibilities for life itself. The same force that rips through space also creates the very ingredients that make existence possible. So what's more powerful, the violence of a supernova or the silent, relentless pull of gravity that gathers dust and gas into newborn solar systems? And then there's the strange, invisible player in this cosmic game, dark energy. It's not explosive, not flashy, but it's pushing the entire universe apart faster and faster. No explosion, no collision, just a quiet force so immense that it dictates the fate of everything. Compared to that, even the mightiest supernova is just a spark in the dark. Power, in the end, isn't just about scale. It's about influence, the forces that don't just exist, the ones that shape reality itself. And when we look at the universe that way, the real question isn't just what's powerful, but what's truly shaping the cosmos. Because sometimes the most powerful thing isn't the loudest, it's the force that works in the background, unseen but undeniable. Black holes are like the universe's ultimate enforcers, silent, relentless, and completely unforgiving. Imagine taking the mass of an entire star, crushing it down to a point smaller than an atom, and packing so much gravity into that tiny space that nothing, not even light, can resist its pull. That's what makes black holes such terrifying cosmic predators. They don't just consume matter, they warp the very fabric of reality around them. Let's break down how these monsters form. Most black holes are born from the violent deaths of massive stars. When a star much larger than our Sun runs out of fuel, it doesn't just fade away, it collapses under its own gravity in a fraction of a second. The outer layers explode outward in a supernova, but the core, it keeps collapsing until it becomes so dense that space and time around it distort beyond recognition. Suddenly, you have a singularity, a point where the laws of physics as we know them break down completely. But the real terror begins once a black hole is active. Their gravitational grip is so absolute that anything crossing their event horizon, the point of no return, is doomed. Stars, gas clouds, even other black holes get stretched, shredded, and ultimately consumed in a process called spaghettification. Picture a star getting pulled in. First, it's stretched into a long, thin strand of plasma like cosmic spaghetti. Then, as it spirals closer, friction heats it to millions of degrees, creating blazing jets of energy that can be seen across the universe. Even light isn't safe. Black holes don't just trap photons, they bend their paths, creating eerie visual distortions. If you somehow survived watching from a safe distance, you'd see light from stars behind the black hole warped into strange rings and arcs, as if the cosmos itself were being reflected in a funhouse mirror. This effect, called gravitational lensing, is one of the most mind-bending proofs of Einstein's theory of relativity. Yet for all their destructive power, black holes also play a crucial role in shaping the universe. Supermassive black holes lurking at the centers of galaxies act like cosmic anchors. Their gravity keeps entire galaxies from flying apart, and some scientists believe they may even trigger the birth of new stars by stirring up gas clouds with their immense energy. So while they devour with one hand, they create with the other, a paradox that makes them even more fascinating. In the grand contest for the title of the universe's most powerful force, black holes are strong contenders. They don't just destroy, they shape, they influence, they rewrite the rules. And yet, as dominant as they are, they're not invincible. They slowly lose energy over billions of years through something called Hawking radiation, a whisper of particles escaping their grasp. Even the mightiest forces in the cosmos have limits, and that's what makes the universe such a beautifully balanced, endlessly surprising place. Not all black holes are created equal. Some are cosmic heavyweights, while others are mere shadows of their larger cousins. Take Sagittarius, a star, the supermassive black hole at the heart of our Milky Way. It tips the scales at a staggering 4 million times the mass of our Sun, yet it's practically invisible against the backdrop of space. Compare that to a typical stellar black hole, the remnants of a collapsed star, which might weigh just 10 to 20 solar masses. The difference isn't just about size, it's about how they shape the cosmos around them. Stellar black holes are born from chaos, the explosive death throes of massive stars. When these stars collapse, they leave behind a gravitational trap so intense that nearby matter gets sucked in like water spiraling down a drain. But despite their fearsome reputation, their influence is local. They might devour a passing star or two, warping space in their immediate vicinity, but they don't hold sway over entire galaxies. Supermassive black holes, on the other hand, are the undisputed rulers of their domains. Most galaxies have one at their center, and their gravity acts like an invisible hand guiding the motion of billions of stars. Sagittarius, a star, for example, doesn't just sit quietly. It whips nearby stars into frenzied orbits at speeds of thousands of miles per second. These monsters didn't form from single collapsing stars. They grew over billions of years, feasting on gas, dust, and even other black holes. Some might have started as tiny seeds in the early universe, swelling in size as galaxies formed around them. What's truly fascinating is their role in galaxy evolution. Supermassive black holes aren't just destroyers, they're cosmic sculptors. When they feed, they unleash torrents of energy that can heat surrounding gas so intensely it stops new stars from forming. This might sound destructive, but it's actually a balancing act. Without this regulation, galaxies could overproduce stars, burning through their fuel too quickly. In some cases, the jets of matter shooting from these black holes can even trigger star birth by compressing distant gas clouds. Stellar black holes, while smaller, have their own dramatic flair. When two of them collide, they send ripples through spacetime itself, gravitational waves so powerful we can detect them here on Earth. These collisions are some of the most energetic events in the universe, briefly outshining entire galaxies. Yet, for all their violence, they lack the long-term influence of their supermassive cousins. So which is more powerful, a supermassive black hole bending an entire galaxy to its will, or a stellar black hole tearing through space-time in a cataclysmic merger? The answer might depend on how you define power. One shapes the universe on a grand scale, while the other reminds us of the raw, untamed energy lurking in the darkness. Together, they show us that black holes aren't just cosmic vacuum cleaners, they're fundamental architects of the universe. If black holes are the universe's silent predators, quasars are their screaming counterparts, cosmic beacons so brilliant they outshine entire galaxies. These dazzling objects are actually the ultra-luminous cores of young galaxies, where supermassive black holes feast on unimaginable amounts of gas and dust. But unlike their quieter cousins, quasars don't dine discreetly. They announce their presence with jets of energy so intense they can be seen clear across the observable universe. To grasp the sheer scale of a quasar's power, think of our Sun, a star that bathes our solar system in light and warmth. Now multiply that energy by 1 trillion, and you're still only scratching the surface. A single quasar can emit more light than every star in the Milky Way combined, all from a region no larger than our solar system. That's not just bright, it's like comparing a candle to a supernova. So how do these cosmic powerhouses work? At the heart of every quasar lies a supermassive black hole, but with a twist, it's not just sitting idle. As vast clouds of gas spiral inward, friction heats them to millions of degrees, creating a swirling disk of incandescent plasma. This accretion disk glows so fiercely it outshines the galaxy around it. But the real spectacle happens at the poles, where magnetic fields funnel some of that material into jets shooting outward at nearly the speed of light. These jets stretch for thousands of light years, carving through space like cosmic blowtorches. What's truly staggering is their role in the early universe. Quasars were far more common billions of years ago, when galaxies were young and packed with fresh fuel for their ravenous black holes. The most distant quasar we've spotted, J0314, burns so brightly it's visible from over 13 billion light-years away, meaning we're seeing it as it was when the universe was just a toddler. Yet for all their brilliance, quasars are fleeting. As their black holes consume the surrounding gas, the show slowly dims. Many of the supermassive black holes we see today in nearby galaxies, including our own, might have once been quasars, now quiet after exhausting their colossal meals. That's the irony of cosmic power. The most spectacular displays often mark a brief, fiery youth before settling into a more sedate adulthood. Quasars remind us that power isn't just about raw strength, it's about transformation. They take the chaos of falling matter and turn it into light so intense it defies belief. And in doing so, they illuminate not just the darkness of space, but the dynamic, ever-changing nature of the universe itself. Gamma-ray bursts are like the universe's ultimate fireworks, except instead of light and color, they unleash torrents of death. These are the most violent explosions since the Big Bang itself, and they make supernova look like birthday candles. In just a few seconds, a single gamma-ray burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. That's not just power, that's annihilation on a cosmic scale. So where do these terrifying blasts come from? Most originate from two catastrophic scenarios. The first involves the explosive deaths of hypergiant stars, supernova on steroids called hypernova. When a star dozens of times more massive than our Sun collapses, it doesn't just explode outward. Its core implodes into a black hole so rapidly that it shoots out twin jets of plasma at near light speed. These jets, packed with gamma radiation, punch through the dying star's outer layers and blast into space, creating a beam of pure destruction so focused it could vaporize a planet from thousands of light years away. The second source is even more exotic: neutron star collisions. Imagine two city-sized remnants of dead stars, each so dense a teaspoon of their material weighs 1 billion tons, spiraling toward each other in a deadly dance. When they finally collide, the impact ripples spacetime itself, splashing out a tsunami of gamma rays alongside gravitational waves. These mergers forge gold, platinum, and other heavy elements in their wake, proof that even the universe's most violent events can seed creation amid chaos. Here's what makes gamma-ray bursts truly chilling: their reach. A beam from one of these events striking a planet head-on would strip its atmosphere like sandblasting paint off metal. The ozone layer would vanish instantly, exposing life to lethal ultraviolet radiation. The sky would ignite in chemical fires, and high-energy particles would rain down, mutating DNA beyond recognition. Some scientists believe a gamma-ray burst might have contributed to Earth's Ordovician mass extinction 450 million years ago, wiping out nearly 85% of marine species. Yet for all their destructive potential, gamma-ray bursts serve as cosmic lighthouses. Their brief flashes help astronomers map the distant universe, probing regions too faint to see otherwise. The farthest burst ever detected, GRB 090429b, erupted just 630 million years after the Big Bang, offering a glimpse into the universe's fiery adolescence. What's sobering is the randomness. A gamma-ray burst could be happening right now in a galaxy millions of light years away, its deadly beam already racing toward us. The odds are vanishingly small, but it's a reminder that the universe doesn't care about life's fragility. In the grand contest for ultimate power, gamma-ray bursts are nature's way of showing us just how small we really are, and how lucky we are to exist in a quiet corner of spacetime, at least for now. Imagine a force so pervasive, so overwhelming, that it makes up nearly 70% of the entire universe, yet you can't see it, touch it, or even detect it directly. This is dark energy, the greatest unsolved mystery in modern cosmology. Unlike black holes or quasars, it doesn't announce itself with dazzling displays of power. Instead, it works in the shadows, silently stretching the fabric of space itself, pushing galaxies apart faster and faster with each passing moment. The story of dark energy begins with a surprise. In the late 1990s, astronomers studying distant supernova made a shocking discovery. The universe wasn't just expanding, as Edwin Hubble had shown decades earlier. It was accelerating. This was like tossing a ball into the air, only to watch it shoot upward faster and faster instead of falling back down. The only explanation: some invisible force was working against gravity, driving the cosmos apart. That force became known as dark energy. What makes dark energy so baffling is its nature. We know it's there because of its effects: galaxies racing away from each other, the cosmic microwave background revealing its imprint, but we have no idea what it actually is. One leading theory suggests it's a property of space itself, a sort of cosmic pressure baked into the vacuum. Empty space, according to quantum mechanics, isn't truly empty. It's a seething froth of virtual particles popping in and out of existence. Could this quantum activity be fueling the expansion? Maybe, but the math doesn't quite add up. The predicted energy is a staggering 10 to the power of 120 times stronger than what we observe. That's the worst prediction in the history of science. Another idea ties dark energy to an elusive field called quintessence, a dynamic force that changes over time. Unlike a static vacuum energy, quintessence could wax and wane, altering the fate of the universe. But here's the unsettling part. If dark energy continues to dominate, the universe might face a bleak future. Galaxies will vanish over the horizon, their light stretched beyond detection. Eventually, even atoms could be ripped apart in a catastrophic Big Rip, where space itself tears at every scale. Yet for all its mystery, dark energy holds a strange beauty. It's the reason we live in a golden age of cosmology, where the universe is still transparent enough to study. Billions of years from now, as space stretches thinner, future civilizations might look up at an empty sky, their view of the cosmos erased by dark energy's relentless push. We're lucky to exist in this fleeting window where the universe is both knowable and breathtakingly vast, a reminder that some of the most powerful forces aren't just invisible, they're the very framework of reality itself. While dark energy is stretching the universe apart, its mysterious counterpart, dark matter, works in silent opposition, holding everything together. Imagine a cosmic glue, invisible and intangible, yet so powerful that without it, galaxies would fly apart like spinning tops losing their balance. Dark matter doesn't shine, absorb, or reflect light. It doesn't interact with electromagnetic forces at all, yet its gravitational pull binds stars, gas, and entire galaxies into the structures we see today. This isn't just a passive force, it's the universe's unseen architect shaping the cosmos from the shadows. The first clues to dark matter's existence came from the way galaxies move. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma cluster, a group of galaxies speeding around so fast that their visible mass couldn't possibly hold them together. The math was clear. There had to be something else, something invisible, providing the extra gravity. Decades later, Vera Rubin found the same anomaly in individual galaxies. Stars at the edges of spiral galaxies orbited just as fast as those near the center, defying Newton's laws. The only explanation, an enormous halo of dark matter, enveloping each galaxy like an invisible fist, keeping everything in place. What makes dark matter so fascinating is its dual nature. Unlike black holes or gamma-ray bursts, it doesn't destroy, it builds. In the early universe, tiny clumps of dark matter acted as gravitational seeds, pulling in ordinary matter to form the first galaxies. Without it, the cosmos might have remained a shapeless sea of gas, never condensing into the brilliant structures we see today. Even now, dark matter's fingerprints are everywhere. The intricate cosmic web, vast filaments of galaxies spanning billions of light years, owes its structure to dark matter's gravitational scaffolding. Yet for all its constructive power, dark matter remains frustratingly elusive. Scientists have proposed countless candidates: WIMP, weakly interacting massive particles, actions, even primordial black holes, but so far, none have been directly detected. Experiments deep underground, in abandoned mines and tunnels, hunt for rare collisions between dark matter particles and ordinary atoms. Space telescopes map its distribution by observing how its gravity bends light from distant galaxies. Every clue brings us closer, but the mystery endures. The irony is profound. Dark energy pushes the universe toward dispersion and cold oblivion, while dark matter pulls it into ordered structures, a cosmic tug-of-war playing out over billions of years. One threatens to unravel everything, the other quietly holds it all together. Together, they remind us that the most powerful forces aren't always the loudest. Sometimes they're the ones we can't even see. Neutron stars are the universe's ultimate pressure cookers, cosmic objects so dense they defy common sense. Picture crushing the entire mass of our sun into a sphere no wider than Manhattan. The result, a single teaspoon of neutron star material, would weigh over 1 billion tons on Earth, more than all the cars, buildings, and mountains on our planet combined. This isn't just dense, it's matter pushed to the brink of impossibility, where atoms themselves collapse into a sea of neutrons packed shoulder to shoulder. But neutron stars aren't just about mind-boggling density. They're also cosmic powerhouses of magnetism and motion. Take magnetars, a rare and terrifying breed of neutron star with magnetic fields so strong they'd erase the data from every credit card on Earth from halfway across the galaxy. These fields are a quadrillion times more intense than our planet's, capable of twisting the star's crust like taffy, triggering starquakes that release bursts of X-rays and gamma rays. In 2004, a magnetar 50,000 light-years away unleashed a flare so bright it temporarily ionized Earth's upper atmosphere, despite being far beyond our solar system. Then there's the dance of death some neutron stars perform. When two of them orbit each other, they don't just spiral quietly into the darkness. They warp spacetime itself, sending out ripples called gravitational waves, a phenomenon predicted by Einstein a century before we finally detected it in 2015. The collision of two neutron stars isn't just a spectacle, it's a cosmic alchemy lab. These mergers forge heavy elements like gold, platinum, and uranium in their violent aftermath, scattering them across the universe. That gold ring on your finger, it might have been born in the heart of a neutron star collision billions of years ago. What's astonishing is how these stellar corpses reveal the extremes of physics. Neutron stars spin at dizzying speeds. Some rotate hundreds of times per second, their surfaces moving at a significant fraction of light speed. Pulses of radiation beam from their magnetic poles like cosmic lighthouses, creating pulsars that tick with precision rivaling atomic clocks. Yet for all their ferocity, they're also fleeting. Given enough time, even neutron stars will cool and fade, their incredible energy slowly leaching away into the void. In the contest for cosmic supremacy, neutron stars may not be the largest or the flashiest, but they're proof that power isn't just about scale. It's about what happens when the universe takes ordinary matter and pushes it beyond every limit we know. They're reminders that even in death, stars can become something extraordinary. A supernova isn't just a star's death. It's a cosmic rebirth, a fleeting moment where destruction and creation collide on an unimaginable scale. Picture a star hundreds of times more massive than our Sun, reaching the end of its life. For millions of years, it's burned bright, fusing atoms in its core to stay alive. But when the fuel runs out, the balance shatters. In seconds, gravity wins. The star collapses inward, then rebounds in a cataclysm so violent it outshines entire galaxies. This explosion doesn't just obliterate, it transforms. The energy released is so intense that it forges elements heavier than iron, scattering them like cosmic seeds across space. Every gold necklace, every iron nail, even the calcium in your bones, they all trace back to these stellar explosions. Stars can't create these heavy elements during their lifetimes. Fusion stops at iron. But in the heart of a supernova, temperatures soar beyond 100 billion degrees, and atoms are bombarded with neutrons so fiercely they fuse into gold, platinum, uranium. The shockwave hurls this newly forged material outward at millions of miles per hour, seeding nebulae with the building blocks of planets and life. Our solar system formed from a cloud enriched by such an explosion long ago. In a very real sense, we're made of stardust, the remnants of a star that died billions of years before Earth existed. Yet the story doesn't end with chemistry. Supernovae are also cosmic sculptors. The shock waves from these blasts rip through nearby gas clouds, compressing them so tightly they collapse into new stars. The Orion Nebula, a stellar nursery visible to the naked eye, may owe its star-forming frenzy to an ancient supernova's lingering push. It's a staggering cycle. Death breathes life, destruction fuels creation. Even the remnants left behind neutron stars or black holes become gravitational anchors, shaping the orbits of future worlds. But here's the twist: not all supernovae are the same. Some, like type Roman II, come from the collapse of massive stars. Others, type Ia, occur when a white dwarf steals so much mass from a companion star that it detonates like a thermonuclear bomb. These explosions are so uniform in brightness they're used as cosmic yardsticks, helping astronomers measure the expansion of the universe. It was studying Type Ia supernova that revealed dark energy's existence, proving how even in death, stars illuminate the universe's deepest mysteries. Supernova remind us that power isn't just about force, it's about legacy. A single explosion might last mere weeks in the sky, but its echoes shape the cosmos for eons. Without these stellar deaths, the universe would lack the complexity for planets, oceans, or life. The iron in our blood, the silicon in our rocks, the very air we breathe, they all whisper the story of stars that died so we could exist. And somewhere out there, another supernova is preparing to ignite, continuing the cycle that turns ashes into worlds. The universe wasn't always filled with black holes, quasars, or swirling galaxies. It began with a single, unimaginable surge of power. The Big Bang wasn't just an explosion. It was the birth of reality itself, an eruption of energy so vast that everything we see today, every star, every planet, every atom traces back to that fiery moment. And here's the wild part, we can still see its echoes. Picture the universe squeezed into a space smaller than a single atom, hotter and denser than anything we could recreate. Then, in a fraction of a second, it expanded faster than light itself, not into space but creating space as it went. This wasn't fire bursting outward like a bomb. It was spacetime stretching, cooling, and settling into the cosmos we recognize. Within minutes, the first atoms formed, hydrogen and helium, the fuel for every future star. But the real proof of this cosmic genesis isn't just theoretical, it's written in the faint glow that fills the sky. That glow is the cosmic microwave background radiation, or CMB, the oldest light in the universe, released when the cosmos cooled enough to become transparent, about 380,000 years after the Big Bang. Today, it's just a whisper of microwaves, barely warmer than absolute zero, but it's everywhere. Point a radio telescope at the emptiest patch of sky, and you'll hear the static of this ancient afterglow, a snapshot of the infant universe. The tiny fluctuations in its temperature, those are the seeds of all structure, slightly denser regions where gravity would later pull matter into galaxies and galaxy clusters. Yet the Big Bang's power isn't just in what it created, it's in what it left unfinished. The universe kept expanding, and dark energy now drives that expansion faster, but the initial burst set everything in motion. Every black hole's gravity, every supernova's fury, even the nuclear fusion in our sun, all of it owes its existence to the conditions forged in those first moments. Even time itself began here, a concept so profound it bends the mind. There was no before, because the Big Bang didn't happen in space and time, it created them. What's equally staggering is how much we don't know. What triggered the Big Bang? Was it the rebound of a previous universe or something beyond our physics? For all its power, the Big Bang wasn't an end, it was the first domino in an endless cosmic chain, a spark that lit a fire still burning 14 billion years later. And every time we detect a gravitational wave or map the CMB, we're not just studying the past, we're touching the fingerprints of the universe's original, unmatched power. The Big Bang set the universe in motion, but something even more dramatic happened in the moments immediately after. A growth spurt so explosive it makes today's cosmic expansion look sluggish. This was cosmic inflation, a period when the universe didn't just expand, it ballooned exponentially, doubling in size at least 90 times in a fraction of a second. To put that into perspective, if the universe were the size of a grape before inflation, by the time it ended, it would have been larger than the entire observable cosmos we see today. This wasn't just fast, it was a runaway stretch of spacetime itself, driven by a mysterious energy field that temporarily overpowered gravity. What's incredible about inflation isn't just the speed, it's how it solved some of the universe's biggest puzzles. Take the horizon problem. Why does the cosmic microwave background, the afterglow of the Big Bang, look so uniform in all directions? regions of space now billions of light-years apart were once close enough to reach thermal equilibrium before inflation yanked them apart. Then there's the flatness problem. The universe's geometry is eerily balanced between open and closed, like a pencil perfectly poised on its tip. Inflation flattened spacetime by stretching it so violently that any initial curvature became imperceptible, like smoothing out wrinkles on a rapidly expanding balloon. But inflation did more than just tidy up the cosmos. It planted the seeds for everything to come. Quantum fluctuations, those tiny ripples in the fabric of reality, got stretched to cosmic proportions during this rapid expansion. These microscopic wrinkles became the gravitational wells where matter later pooled, forming galaxies and galaxy clusters. In other words, the largest structures in the universe trace back to subatomic tremors magnified by inflation. It's as if the universe took a deep breath, then exhaled itself into existence. The mechanism behind inflation remains one of physics' greatest mysteries. The leading theory involves a hypothetical field called the inflaton, which, like dark energy, permeated space with repulsive gravity. As this field decayed, its energy reheated the universe, filling it with the hot plasma of particles we recognize from the Big Bang model. But unlike dark energy, which acts as a steady push, inflation was a sprint that ended abruptly, leaving behind the slower, more familiar expansion we see today. Could inflation have been a one-time event, or is our universe just one bubble in an endless multiverse? Some theories suggest that inflation never truly stopped, it just paused in our pocket of reality, while other regions continue expanding eternally, spawning infinite universes with different physical laws. Whether or not that's true, one thing is certain: inflation was the universe's ultimate power play, a fleeting but transformative burst that set the stage for everything from the tiniest atoms to the grandest galactic superclusters. And without it, the cosmos as we know it might not exist at all. Among all the universe's destructive forces, none is more chillingly efficient than vacuum decay, a hypothetical disaster where the very laws of physics could unravel in an instant. Picture the universe as a fragile balancing act perched atop a precarious energy state. What if it's not in the lowest possible energy configuration? What if somewhere out there, a deeper, more stable vacuum exists, one that our current reality is desperate to collapse into? This isn't science fiction. It's a terrifying possibility rooted in quantum field theory, where a single misstep in the cosmic order could rewrite existence itself. Here's how it might unfold. Imagine a tiny bubble forming somewhere in space, smaller than an atom, where quantum fluctuations trigger a phase transition, like ice melting into water but for spacetime. Inside this bubble, the fundamental constants we take for granted, the speed of light, the strength of gravity, even the behavior of particles, could suddenly change. The bubble would expand at light speed, its walls rewriting physics as they go. By the time the light from this catastrophe reached your eyes, it would already be too late. The wave of destruction would erase atoms, stars, and life itself before anyone could blink. The scariest part, we wouldn't see it coming. Vacuum decay could start anywhere, anytime, triggered by a random quantum event or even human experiments with high-energy particle collisions. Unlike a supernova or gamma-ray burst, there'd be no warning, no time to react. One moment, the universe is as we know it. The next, everything is gone, replaced by a new reality governed by alien physics. Even black holes would be powerless against it. Their immense gravity couldn't stop a change that rewrites the rules of spacetime itself. Yet there's a strange beauty in this doomsday scenario. It hints at a deeper truth about our universe. The laws we consider absolute might just be a temporary arrangement, a local minimum in an infinitely complex energy landscape. Some theories even suggest this has happened before, that our universe is just one in a chain of cosmic reboots, each born from the ashes of a previous vacuum collapse. For now, vacuum decay remains speculative. No evidence suggests our vacuum is unstable, and the odds of it spontaneously collapsing are astronomically low. But the mere possibility forces us to confront how little we truly understand about the fabric of reality. It's a reminder that for all its apparent stability, the universe might be balancing on a knife's edge, and the slightest nudge could send it tumbling into the abyss. At the smallest scales imaginable, the universe is far from empty. It's a seething, bubbling cauldron of activity where particles blink into existence and vanish again in less than a heartbeat. These are quantum fluctuations, tiny ripples in the fabric of reality where energy briefly transforms into matter, creating particle-antiparticle pairs that annihilate each other almost instantly. It sounds like science fiction, but this isn't just theory. It's been observed in laboratories. And here's the astonishing part. These fleeting events might hold the key to understanding some of the universe's grandest mysteries. Consider the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a subtle push. Why? Because the space between them is so narrow that certain quantum fluctuations can't fit, creating a pressure difference. Outside the plates, particles and antiparticles pop in and out of existence freely, but inside, their dance is restricted. The result: the plates move toward each other as if squeezed by the invisible hands of quantum mechanics. This isn't just a lab curiosity, it's proof that empty space isn't empty at all. It's a dynamic arena where energy and matter trade places in an endless, invisible ballet. Now scale this up to cosmic proportions. During inflation, those same quantum fluctuations didn't just vanish. They were stretched across the universe, frozen into the fabric of spacetime as microscopic density variations. These became the seeds for all cosmic structure, the slight overdensities where gravity later pooled matter into galaxies and clusters. The galaxies we see today, the vast cosmic web spanning billions of light years, it all traces back to quantum tremors smaller than an atom. But the influence of quantum fluctuations doesn't stop there. Near the event horizon of a black hole, things get even wilder. Particle-antiparticle pairs emerging from the vacuum can get separated, with one particle falling into the black hole while the other escapes as radiation. This is Hawking radiation, the process that slowly evaporates black holes over eons. Think about that. The universe's most fearsome predators are gradually dissolving because of tiny quantum hiccups at their edges. Perhaps the most mind-bending implication is the role these fluctuations might play in the universe's ultimate fate. If a particularly large quantum fluctuation occurred in just the right way, it could trigger a new Big Bang, or worse, vacuum decay. The same mechanism that helped build the cosmos could also unmake it, a humbling reminder of how deeply interconnected the smallest and largest scales truly are. Quantum fluctuations might be invisible, fleeting, and impossibly small, but their echoes shape everything from the atoms in your body to the fate of the universe itself. Deep within the fabric of the universe lies an invisible field so fundamental that without it, nothing would have mass, not stars, not planets, not even you. This is the Higgs field, the cosmic architect of weight and structure. Think of it like an endless, invisible ocean filling all of space. As particles move through it, some interact more strongly than others, slowing them down and giving them mass, like wading through thick syrup instead of empty air. Electrons, quarks, even the building blocks of atoms all get their heft from this interaction. Without the Higgs field, particles would zip around at light speed, never clumping together to form matter as we know it. The discovery of the Higgs boson in 2012 at the Large Hadron Collider was a landmark moment, proof that this field wasn't just theoretical. The boson itself is like a ripple in the Higgs field, a fleeting disturbance created when enough energy is pumped into the system. But here's the twist: the Higgs field isn't just a passive backdrop. Its energy state might hold the key to one of the universe's most existential threats, vacuum decay. Right now, the Higgs field exists in what physicists call a false vacuum, a stable but not perfectly stable state. It's like a marble resting in a shallow dip on a hillside, seemingly secure, but with the potential to roll into a much lower valley if given a nudge. If the field were to suddenly drop to its true lowest energy state, the rules of physics as we know them could change instantly. The speed of light, the strength of gravity, even the behavior of atoms might be rewritten in a cascading wave of transformation. What's eerie is how this ties back to the birth of the universe. During cosmic inflation, the Higgs field might have briefly been in a higher energy state, driving the exponential expansion of spacetime before settling into its current form. But if it could shift once, could it shift again? The unsettling answer is yes, though the odds are vanishingly small. A high-energy particle collision, a quantum fluctuation, or even random chance could, in theory, trigger this catastrophic transition. Yet the Higgs field isn't just a cosmic time bomb, it's also a testament to elegance. Its existence solves one of physics' greatest puzzles: why particles have mass at all. Without it, the universe would be a sea of weightless particles flashing by at light speed, never forming the stars, planets, or life that define our reality. It's a reminder that the most powerful forces aren't always the loudest or most destructive. Sometimes they're the silent shapers, the unseen hands guiding the universe's grand design, and in the case of the Higgs field, quite literally holding it all together. Gravity is the universe's greatest cosmic joke, a force so weak you can defy it by picking up a pebble, yet so powerful it bends light, crushes stars into black holes, and holds entire galaxies together. On the surface, this doesn't make sense. Compare it to electromagnetism, the force that binds atoms and lets you stick a magnet to your fridge without effort. At the atomic level, electromagnetism is a trillion times stronger than gravity. So why doesn't our planet instantly vaporize under that overwhelming force? Because gravity has a secret weapon: it only pulls. Unlike electromagnetism, which can both attract and repel, or the strong nuclear force that fades almost instantly outside an atom's core, gravity is relentless. It never cancels out, never turns off, and given enough time and mass, its influence becomes unstoppable. Think of it like a slow-motion avalanche. A single snowflake is weightless, but pile enough of them together, and their collective pull becomes an unstoppable cascade. Gravity works the same way. The Earth's mass might make the force between you and the ground seem trivial, but scale it up to something like Jupiter, a planet so massive it tugs asteroids into orbit just by existing, and gravity's quiet persistence starts to reveal its true nature. And then there are black holes, where gravity finally drops the act entirely, warping spacetime so severely that even time itself slows to a crawl near their event horizons. What's truly fascinating is how gravity's weakness hides its cosmic dominance. Because it doesn't diminish over distance, its influence accumulates across unfathomable scales. The Andromeda Galaxy, 2.5 million light-years away, is still gravitationally bound to the Milky Way, inching closer for a collision 4 billion years from now. The same force that lets a toddler knock over a block tower also orchestrates the dance of galaxy clusters spanning hundreds of millions of light-years. Yet gravity's reign might not last forever. Dark energy, that mysterious force accelerating the universe's expansion, is essentially gravity's opposite: a repulsive push that could one day stretch the cosmos so thin that even galaxies unravel. For now, though, gravity remains the universe's silent architect, shaping everything from the orbit of your coffee cup on a table to the fate of superclusters drifting in the cosmic dark. It's proof that power isn't always about brute strength. Sometimes it's about patience, persistence, and the quiet certainty that, given enough time, even the faintest pull can move mountains. Cosmic strings sound like something out of science fiction, threads so thin they're nearly one-dimensional, yet dense enough to bend the fabric of spacetime itself. Picture a crack in the ice of reality, an imperfection left over from the universe's earliest moments, when the cosmos was still cooling from the Big Bang's unimaginable heat. These aren't just theoretical oddities, they're relics of a time when the fundamental forces of nature were still sorting themselves out, like wrinkles frozen into a sheet as it settles. And if they exist, their influence would be nothing short of breathtaking. Imagine a strand thinner than a proton but stretching across billions of light years, heavier than entire galaxies. The gravity of such an object would warp space around it so severely that light passing by would bend, creating double images of distant stars, a natural cosmic lens sharper than anything a telescope could replicate. If a cosmic string slid through our solar system, we might not even notice its presence at first until the stars behind it began to appear in duplicate, or the orbits of planets subtly shifted without explanation. But the real mind-bender is how these strings could warp time itself. Moving near the speed of light, a cosmic string could twist spacetime into closed loops, creating pathways that defy our everyday intuition. In theory, two strings intersecting or vibrating in just the right way might forge a time machine, bending causality into a knot where the past and future blur. Of course, the energy required to manipulate strings like this is beyond anything we could muster, assuming they exist at all. The hunt for cosmic strings is as elusive as the objects themselves. Astronomers search for their fingerprints in the cosmic microwave background, looking for telltale temperature fluctuations or strange gravitational lensing patterns that betray their presence. So far, no definitive evidence has emerged, but the possibility remains tantalizing. After all, the universe has a habit of surprising us with phenomena we once thought impossible. Black holes were once mere mathematical curiosities until we found them lurking in the hearts of galaxies. Cosmic strings remind us that the universe's most powerful forces aren't always the most obvious. They could be hiding in plain sight, woven into the fabric of reality so seamlessly that we've yet to detect them. And if they're out there, they're not just remnants of the cosmos's fiery birth, they're threads in a grand tapestry we're only beginning to unravel. Neutrinos are the universe's ultimate ghost particles, so elusive they pass through entire planets like they're not even there. Every second, trillions of them stream through your body at nearly the speed of light, leaving no trace behind. They're smaller than atoms, with masses so tiny we still don't know exactly how little they weigh. Yet despite their near invisibility, neutrinos wield staggering power, especially when it comes to the cataclysmic deaths of stars. Take a supernova, for instance. When a massive star collapses, the core doesn't just implode, it rebounds in a shockwave so violent it blasts the outer layers into space. But here's the twist: most of the energy from that explosion isn't carried by light, heat, or even matter. It's neutrinos. In the first 10 seconds of a supernova, these tiny particles emit more energy than our sun will in its entire 10 billion-year lifetime. They surge outward like a cosmic tsunami, outnumbering every atom in the visible universe combined. Without neutrinos, the shockwave wouldn't have enough energy to rip the star apart. They're the silent architects of stellar destruction. What makes neutrinos so fascinating is their ability to ignore almost everything. Unlike light, which gets absorbed or scattered by cosmic dust, neutrinos travel unimpeded across billions of light years. When supernova 1987 exploded in a nearby galaxy, the light took hours to reach Earth, but the neutrinos arrived first, slipping effortlessly through the star's dense outer layers long before the blast became visible. Detectors buried deep underground, shielded by miles of rock, caught a fleeting pulse of just 24 neutrinos. That faint signal was enough to revolutionize astrophysics, confirming theories about how stars die and how elements like gold and uranium are forged in the chaos. But neutrinos aren't just cosmic bystanders, they might hold clues to the universe's greatest mysteries. Some theories suggest they could explain why the cosmos is made of matter instead of antimatter. In the early universe, slight differences in neutrino behavior might have tipped the scales, allowing particles to outnumber antiparticles and giving rise to everything we see today. Others speculate that relic neutrinos from the Big Bang, now cooled to near absolute zero, could be the missing dark matter hiding in plain sight. For all their subtlety, neutrinos are proof that the universe's most powerful forces don't always come with fanfare. They're the quiet giants, the unseen currents shaping the cosmos from behind the scenes, and as we learn to detect them better, building ever more sensitive observatories in abandoned mines and Antarctic ice, we're not just studying particles. We're decoding the hidden language of the stars themselves. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing billions of stars, many likely hosting planets just as suitable for life as Earth. Given those numbers, the cosmos should be teeming with civilizations, their signals buzzing across the stars. Yet when we listen, all we hear is silence. This eerie contradiction is the Fermi paradox, a puzzle that asks, if intelligent life is probable, where is everybody? One chilling possibility is that the universe itself is a minefield, littered with cosmic traps that snuff out civilizations before they can spread. These are the great filters, catastrophic events or natural barriers so deadly they prevent life from reaching interstellar scales. Imagine gamma-ray bursts, those universe-sculpting explosions we discussed earlier, sterilizing entire galaxies in a flash. A single burst pointed at a planet could strip its atmosphere, irradiate its surface, and erase millions of years of evolution in seconds. If these events are common enough, they might explain why the cosmos feels so empty, because every time life gets a foothold, the universe hits the reset button. But gamma-ray bursts aren't the only potential filters. Supernova, rogue black holes, even the slow creep of entropy could all play a role. Another dark theory suggests that advanced civilizations inevitably destroy themselves, whether through war, environmental collapse, or technologies they can't control. The same intelligence that lets a species build radio telescopes might also give it the power to engineer its own extinction. Here's the unsettling part: we don't know where the great filter lies. Is it behind us, something rare and difficult like the jump from single-celled life to complex organisms, that we've already passed, or is it ahead, lurking in our future, waiting to wipe us out before we ever leave our solar system? The silence of the universe might be a warning, a cosmic gravestone for civilizations that came before us and fell to forces we don't yet understand. Yet there's another angle to consider. Maybe we're not listening the right way. Advanced civilizations might communicate via neutrino beams or gravitational waves, technologies we're only beginning to explore. Or perhaps they've transcended physical forms, uploading their minds into quantum networks we can't detect. The universe's quiet might not be absence, just a language barrier on a galactic scale. Whatever the answer, the Fermi paradox forces us to confront our place in the cosmos. Are we the first, the last, or simply the only ones, in a universe filled with unfathomable power, from black holes to dark energy? The greatest mystery might not be how these forces shape the stars, but whether they've left any room for us at all. Picture a black hole born not from a dying star, but from pure energy, an object so bizarre it twists the laws of physics inside out. This is a Kugelblitz, German for ball lightning, a theoretical black hole forged when enough light or other radiation is crammed into a single point, warping spacetime so severely that it collapses under its own energy. No collapsing star, no matter, just raw power made tangible, a cosmic paradox where even massless photons become gravitational monsters. At first glance, the idea seems impossible. Black holes, after all, are supposed to be the graves of massive stars, their gravity born from crushed matter. But Einstein's equations reveal a stranger truth. Energy and mass are two sides of the same coin, linked by E equals mc squared. Focus enough energy, whether light, heat, or even radiation, into a tiny enough volume, and that energy alone can curve spacetime into an event horizon. The threshold, a mind-bending concentration of energy equivalent to the sun's entire output for months, squeezed into a space smaller than an atom. Now imagine the possibilities. A Q blitz wouldn't just be a cosmic curiosity, it could be the ultimate power source. Unlike ordinary black holes, which slowly leak away via Hawking radiation over eons, a Q blitz made from concentrated lasers or gamma rays might be small enough to evaporate explosively, converting its mass energy back into usable radiation. In theory, a civilization advanced enough to create one could harness this energy, turning black holes into batteries of unimaginable density. A Q blitz the size of a proton could power a city for years, offering clean, nearly limitless energy if you could contain it. But here's the catch: containment is the stuff of nightmares. A Q blitz would be hotter than the core of a supernova, its event horizon sizzling with temperatures in the billions of degrees. Any containment failure wouldn't just mean an explosion, it would mean an artificial black hole drifting uncontrolled, devouring anything in its path. The same physics that makes these objects potential powerhouses also makes them existential risks, balancing on the knife's edge between breakthrough and doomsday. Beyond engineering challenges, Q blitz black holes hint at deeper cosmic truths. They blur the line between matter and energy, suggesting that the universe's most extreme phenomena might not depend on stuff we can hold or see. If energy alone can warp spacetime so severely, what does that say about the nature of gravity itself? Could the Big Bang, a singularity of pure energy, have been the universe's first and greatest Q blitz? For now, these questions remain in the realm of theory. No known natural process concentrates energy tightly enough to spawn a Q blitz, and our technology is light years away from attempting it. But they remind us that the universe's rulebook is far stranger than we've yet uncovered. In a cosmos where even light can become a gravitational prison, the most powerful forces might not be the ones we can hold, but the ones we can barely imagine. Time flows like an arrow, relentless and unyielding, carving the universe into a sequence of irreversible moments. Unlike black holes or supernova, time doesn't crush or explode. It simply passes, carrying everything with it in a current that nothing can escape. From the birth of stars to the decay of atoms, time is the silent architect of change, the force that turns possibility into history. And here's the unsettling truth. Time doesn't just move forward, it drags the entire cosmos toward disorder, a fate dictated by entropy, the universe's slow unraveling into chaos. Think of a sandcastle on a beach. Left alone, it doesn't stay pristine, it crumbles, grains scattering in the wind. That's entropy in action, the natural tendency of systems to break down, energy to disperse, structure to fade. Stars burn out, mountains erode, even black holes evaporate over eons. Time ensures that every ordered system, no matter how grand, will eventually succumb to this cosmic decay. The universe began in a state of perfect order, a hot, dense singularity, and has been sliding toward disorder ever since. Entropy isn't just a law of physics, it's time's signature, written into the fabric of reality itself. Yet time's power isn't just about destruction. It's also the canvas on which the universe paints its most breathtaking creations. Without time's forward march, there would be no evolution, no galaxies spiraling into existence, no life emerging from stardust. A single moment frozen forever would be a universe without stories, without change, a snapshot without meaning. Time's flow is what allows complexity to arise from simplicity, beauty from chaos. The same force that erodes mountains also gives rivers their winding paths. The same current that extinguishes stars once lit them in the first place. Could time itself be the ultimate force? Unlike gravity or dark energy, it doesn't push or pull, it simply is, the stage on which all other phenomena play out. Even the mightiest black hole can't rewind a single second, and no amount of energy can reverse entropy's rise. The universe's expansion may accelerate, galaxies may collide, but time remains the one constant, indifferent to the dramas unfolding within it. Perhaps the most humbling thought is this: Time is the one force that binds everything from the fleeting existence of a mayfly to the lifespan of a galaxy. It doesn't discriminate, doesn't pause, doesn't bend. And when the last star fades and the cosmos drifts into darkness, time will still be there, the only witness to a universe that was and then was no more. In the end, every other force, no matter how violent or vast, answers to time's unflinching rhythm. If that isn't power, what is? What if our universe isn't the only one? Imagine a cosmic tapestry woven with countless realities, each operating under entirely different rules, a multiverse where the very concept of power transforms beyond recognition. In one universe, gravity might be 1,000 times stronger, crushing stars into diamonds in moments. In another, light could crawl like molasses, stretching seconds into centuries. The multiverse theory suggests that our cosmic neighborhood might be just one bubble in an infinite foam of realities, each with its own unique physics rewriting what power even means. Consider a reality where the electromagnetic force dominates over gravity. Planets wouldn't orbit stars, they'd be torn apart by electrostatic repulsion, their atoms scattering like dust in a hurricane. Civilizations there might harness lightning as their primary energy source, building cities that float on magnetic levitation rather than solid ground. Now flip the script, envision a universe where dark energy never existed, causing space to collapse inward in a slow-motion crunch. Time itself could run backward there, with entropy decreasing as shattered teacups reassemble and extinguished stars reignite. Some theories propose that each quantum decision spawns a new universe. Every time you flip a coin, two realities branch off, one where it lands heads, another for tails. Scale this up to cosmic events and you get infinite variations. Universes where Earth never formed, where dinosaurs still rule, or where life evolved in completely alien ways. In such a multiverse, power might not reside in stars or black holes, but in the ability to navigate between realities, harvesting energy from collapsing dimensions or borrowing momentum from parallel worlds. The most mind-bending possibility, universes where fundamental constants are so different that matter as we know it can't exist. Picture a cosmos with no weak nuclear force, where stars can't fuse hydrogen and darkness reigns eternal. Or one where the strong force is slightly weaker, preventing atoms from forming at all. In these places, power could manifest as control over the very fabric of dimensional membranes, manipulating the boundaries between realities like a sculptor kneading clay. Yet for all its grandeur, the multiverse remains a haunting enigma. If other universes exist, their light will never reach us, their physics forever untestable. They might as well be myths, except the math suggests otherwise. Quantum fluctuations, cosmic inflation, even string theory all hint that our universe could be one page in an infinite library. And if that's true, then the most powerful force of all might not be inside any single universe, but in the sheer, staggering diversity of existence itself. A cosmic kaleidoscope where every twist creates new laws, new wonders, and new definitions of what power can be. Humanity may seem insignificant against the backdrop of colliding galaxies and evaporating black holes, but don't underestimate our species' knack for turning cosmic impossibilities into engineering challenges. Consider the Dyson sphere, a hypothetical megastructure that could encapsulate an entire star, harvesting its energy output not with solar panels but by surrounding it completely. The idea sounds like science fiction, but the physics checks out. Imagine millions of orbiting habitats or solar collectors arranged in a swarm, capturing every photon a star emits. The energy yield would be staggering enough to power civilizations for millennia, to reshape planets, even to accelerate starships to other galaxies. This isn't just fantasy, it's a logical extension of the same ingenuity that took us from steam engines to particle colliders. Then there's the warp drive, another concept ripped from the pages of theoretical physics. General relativity allows for the bending of spacetime itself, creating a bubble where the fabric of the universe contracts in front of a ship and expands behind it. No breaking the light speed limit, just cheating it by moving space instead of the ship. The catch: it requires exotic matter with negative energy density, something we've never observed. But the math suggests it's not impossible, just improbable. For a civilization willing to harness the energy of stars, rewriting the rules of propulsion might be the next logical step. Yet these dreams collide with brutal cosmic realities. A single gamma-ray burst could sterilize a planet light years away, and dark energy is stretching the universe apart faster than we can explore it. Even if we built Dyson spheres, would we survive long enough to use them? The universe is old, 13.8 billion years old, and we've barely existed for a cosmic blink. Maybe we're not just late to the party, maybe the party is already over. The eerie silence in our search for extraterrestrial intelligence suggests a grim possibility that advanced civilizations inevitably hit a wall, whether environmental collapse, self-destruction, or some universal filter we haven't encountered yet. But here's the other side of the coin. Humanity thrives on adversity. We've already bent fundamental forces to our will, from splitting atoms to genetically editing life itself. The same curiosity that sent us to the moon might one day crack the code of quantum gravity or harness vacuum energy. Sure, we're ants in a storm, but ants build colonies that withstand hurricanes. The universe may be indifferent, but indifference isn't the same as impossibility. The stars don't care if we reach them, but that's exactly why we must try. So where does true cosmic power lie? In the ability to destroy, to create, or to shape the unseen rules of reality itself? Let's weigh the contenders. Black holes are undeniably terrifying, ripping stars apart and warping space-time like cosmic funhouse mirrors. Their gravitational grip is absolute, their hunger insatiable, yet for all their might, they're prisoners of their own nature, bound by the same laws they twist. They devour, but they don't build. A supernova's fury forges the elements of life, but it's a one-time spectacle, a brilliant flash before fading into cosmic history. Then there's the Big Bang, the ultimate act of creation. From a singularity smaller than an atom, it birthed every galaxy, every star, every breath of existence. It didn't just unleash energy, it wrote the laws of physics themselves. Yet here's the paradox: the Big Bang was a moment, not a force. It set the stage but handed the reins to dark energy, inflation, and quantum fluctuations to shape what came next. Which brings us to dark energy, the silent renegade rewriting the universe's fate. Unlike black holes or supernova, it doesn't dazzle or destroy, it simply is, an omnipresent push stretching space itself. It doesn't just influence galaxies, it dictates the cosmos's ultimate destiny. Cold, indifferent, and unstoppable, it's the closest thing the universe has to an unchallenged ruler. But perhaps power isn't about scale or spectacle. Maybe it's about endurance, the quiet, relentless force that outlasts all others. Gravity shaped the cosmos, but dark energy will define its twilight. The Big Bang ignited existence, but quantum fluctuations sowed its structure. Black holes terrify, but time, that inexorable current, wears even them to nothing. In the end, crowning a single victor misses the point. The universe's true power lies in its balance, the interplay of creation and destruction, seen and unseen, fleeting and eternal. Each force is a note in a grand symphony, and without one, the music would fall silent. So forget rankings. The real marvel isn't which force reigns supreme, but how they conspire to craft a cosmos where stars explode, black holes spin, and mysteries like dark energy remind us that the universe still holds its cards close. That's power, not in domination, but in wonder. So what's the verdict? What truly holds the crown as the universe's most powerful force? We've journeyed through cosmic heavyweights, from black holes bending spacetime to supernova seeding life itself. We've marveled at dark energy's silent domination, watched quasars scream across the cosmos, and even dared to imagine Kugelblitz black holes born from pure light. Each contender brings something extraordinary to the table: raw destruction, relentless creation, or the quiet rewriting of reality's rules. But here's the beautiful twist: there might not be a single answer. Power in the universe isn't a solo act, it's a symphony. Gravity sculpts galaxies, but dark energy dictates their fate. Supernova forged the elements, while quantum fluctuations laid their blueprint. Time, the ultimate unifier, marches on as stars explode and black holes evaporate. Maybe the real magic lies in the balance, the way these forces dance together, each playing its part in the grand cosmic story. Now it's your turn. Which force captivates you the most? Is it the terrifying elegance of a black hole, the creative chaos of a supernova, or the eerie silence of dark energy pulling the strings behind the scenes? Drop your pick in the comments. We're all cosmic explorers here, and every perspective adds to the wonder. If this journey through the universe's most mind-bending powers left you hungry for more, don't miss what's next. Hit that subscribe button and ring the bell, because the cosmos is full of mysteries waiting to be unraveled, and we're just getting started. Until then, keep looking up. The universe has a way of surprising those who dare to wonder.